Hello everybody, welcome to session 25. This is going to be a very interesting session. We will talk about the Feynman-Cag theorem and its applications to option pricing. In the previous sections of this part, where we've gone all the way from exotic options, traditional options, Black-Scholes options, etc., we have put a lot of attention in the solution of partial differential equations. At the same time, underlying the notion of a derivative, basically of an option, there is an expected value of a payoff function. So at some point, from a very intuitive level, there seems to be a disconnect between a partial differential equation, which feels more like just calculus, and an expected value of something that feels like statistics. Fortunately, there's a theorem that puts the two things together. This is the Feynman-Cag theorem. So we will go through that and underscore the fact that this theorem will prove to be extremely useful in finding the closed form solutions of some traditional derivatives. As we move ahead in the course, we will find ourselves with some other theorems that are extremely powerful as well, that relate to a special case of stochastic processes. We will talk about those affine jump diffusions later on, but for now, let's concentrate in one of the most interesting and I would say most beautiful theorems for option pricing. Essentially, what this theorem says is that if we start with a partial differential equation, the solution of a partial differential equation that follows this form will be an expected value, a conditional expected value, giving some measure, probability measure Q. And this is conditional on some initial value or some value of the state variable at time t. So the beauty of this is that we will have a connection between a partial differential equation and an expected value. Both things are part of the same concept, but are just two faces of the same coin. I will come back to these, but just let me motivate the class of today by looking at what are the results that we are going to get. So we're going to start from the concept, from the proposition of how a partial differential equation can be related to an expected value and vice versa. Now, as we move on, we will see how this can be used, let's say, for deriving the Black-Scholes equation. So essentially, what we will have is that the general form of the Feynman-Cag partial differential equation can be somehow related to the Black-Scholes partial differential equation. We will build in each one, or for each one of our exercises, a table that essentially maps the general form of the Feynman-Cag with the specific form of the partial differential equation in the model that we are interested in solving. Then, from the general model, where we will have to, as you see, we will follow a constructive approach from some components of the more complicated integral until building the full integral, we will be building all the bits and pieces until reaching the final integral. Now, for the case of the Black-Scholes, it's interesting to see that the equation, the partial differential equation, ends up in this familiar integral, which is nothing but the expected value of the payoff function at terminal time t. Now, obviously, we're not there yet. We will need to compute the conditional expectation that it's here, and we will use Maple to continue and doing all that exercising. So we'll continue calculating the expected value of the conditional expected value of that expression, and finally we will go step by step, so don't get ahead of yourselves, but I just want to show you that eventually we will end up achieving and reaching exactly the Back-Scholes equation, which, to be very honest, in the previous chapters, we just were proving that satisfy the partial differential equation, but we were not able to go all the way from the partial differential equation to this expression. This time around, we will go all the way and finally reach the result. We can do the same for the Vasicek model. So in the Vasicek model, remember that we had a partial differential equation and some boundary conditions. So we will do exactly the same thing. I mean, we will start with the partial differential equation for the Feynman-Kac theorem. Then we will write down again the Vasicek problem. We will map the two. We will end up with a partial differential equation using the notation of the Feynman-Kac. Then we will build our table of equivalences, reach the final expected value, conditional RT, given the probability measure Q, which is essentially defined by the stochastic process. So with some stochastic process, which in this case we will say could be a geometric Brownian motion process, and with a little bit of creative Ito calculus, we can solve this expected value. Assuming, obviously, as I was saying, that R follows this Ito process. We can also explore slightly more complex processes, which are more like the Vasicek model, which in the end is nothing but an Ornstein-Uhlenbeck process. So we do exactly the same, and we will end up with our beautiful equation, which is nothing but the solution to the Vasicek problem in the 1973 paper. So we will scroll back all the way to the top. This is going to be fantastic. So at the end of this class, everything will make sense. We will see how working with partial differential equations and working with conditional expected values is the same thing, and this will give us a lot of freedom in modeling future problems.